Hi, welcome back to Introductory Statistics. In this lecture, we're going to talk about the ChiSquare Test. We'll cover chapter 28 of the textbook. Okay, so let's talk about the ChiSquare Test. This is invented in 1900 by Carl Pearson. Chi is a Greek letter. We pronounce it as chi, as in chi and kite. And so this test is called ChiSquare. And so in chapter 26, we talked about how to apply the test for significance chance model, which is on the ESP experiment. In that example, each guess is classified into one of two categories, whether the guess is correct or not correct. And according to the model, you have a 1 in 4 chance of getting it right. And so you're essentially drawing random tickets from the box 0001. In that case, we saw that the ZTest was appropriate because we only have two categories. But if you have more than two categories, then the ChiSquare test works better than the ZTest. And so, for example, if you want to look at a die and see whether it's fair, every die has 6 categories, numbers 1 to 6. So ChiSquare would be appropriate for this example. Okay, so let's look at an example. So suppose you have a gambler who is accused of using a loaded die, and he pleads innocent, and we look at the record of the last 60 throws from this table. And so how do we interpret this data? How do we know whether the die is loaded based on that table of data? So the ChiSquare test can help us do this. So the gambler is innocent. The numbers in table 1 would be like drawing 60 times at random with replacement from the box 1 to 6. And according to this model, each number should come up 10 times. This is the expected frequency because there's a 1 in 6 chance of getting a certain number, and you do it 60 times, you should get each of the numbers 10 times each. The observed frequencies are shown from table 2. So now we have the observed frequency as well as the expected frequency of 10. And now we want to look at these and figure out whether how far off the observed frequency from the expected frequency. Now notice that we do see that there's a lot of 3's here, right? This 17 it comes up 17 times, but we only expect it to be 10. So you look at one number, then maybe it's off. And the same thing for number 4. 4 comes up 16, which is maybe a little bit too many times. And so let's look at the standard error for each of these. So let's look at only the number of 3's. It comes up 17 times, which is a little bigger than what it should be. So let's figure out how far off that is. Let's find the standard error for the number of 3's. We'll take the root of the number of draws times SD of the box. So remember, SD of the box is just that shortcut formula. If we do this, we get that the SE for the number of 3's is 2.9. That means that 17 is actually 2.4 SEs above 10. So that's far away. So, however, the only thing is we have to be careful that we don't look at one line at a time. So even though 3 is very far away from the expected value, 17 is very far away from the expected value of 10, we can't look at 3 in isolation. We have to look at all 6. And the reason is because even if everything is, even if the die is fair, there's a high chance that at least one of them will look suspicious. And so that's why we need to look at the whole table rather than just one line at a time. Okay, so the ChiSquare formula is going to help us do this. Here's the formula. We're going to take the sum of the observed frequency minus the expected frequency square divided by the expected frequency. So for each line of the table, we take the observed minus the expected, square the answer, divided by the expected, and then we sum all of this up among all rows of the table. So here's how we do that. So 4 is the observed, 10 was expected, subtract it, square that, divide by 10, which is the expected. Do the same thing for 6, which is the observed value, 10 is expected, square that, divide by 10. Do this for the rest of the table, you get 14.2. So this 14.2 tells you how far away is the observed frequency and the expected frequency. The bigger the sum, then the bigger the difference between the expected and the observed. The smaller this answer, then the closer they are. And so again, large value of chi-square indicate that the observed and the expected frequencies are far apart. Small values of chi-square means that the observed and expected are closer, and so this chi-square give a measure of the distance between the observed and the expected frequencies. Okay, but of course, one argument is that, well, maybe 14.2 is not so big, it's just a chance error, right? So we want to know whether what's the chance of getting 14.2 or more, and if we can figure out this chance, we can say something about whether that number is due to a chance or not. So again, this is similar to the last lecture when we talked about the test for significance. We want to look at the evidence against the model, and so we want to look at 14.2 or more, because the values that are larger than 14.2 would be even stronger evidence against the model. Okay, so what's the chance that the model will produce such strong evidence against itself? Well, we got to calculate the chance of getting this chi-square statistics of 14.2 or more. And so it turns out that you can use a computer for this, but we're going to show you how to do that using a table in a second, but it turns out the answer happens to be 1.4%. So that means that if the die was fair, there's only a 1.4% chance of getting chi-square statistics as big as or bigger than the observed value of 14.2. That means that because this p-value is small, then it doesn't look too good for the gambler. Notice this is very similar to the test for significance using the ZTest in the last lecture. In fact, everything's the same except for the chi-square statistic that we use here rather than the Z statistic that we use in that lecture. So this 1.4%, just like the last chapter, is called the observed significance level, the p-value. And so let's talk about how to compute this. So we have a bunch of curves called the chi-square curve that we can use to find this p-value. And this curve depends on a number called the degrees of freedom. And so, for example, here's two curves. The solid curve is for 5 degrees of freedom. The dashed curve is for 10 degrees of freedom. So we're going to define the degrees of freedom in a second. But if I know the degrees of freedom, I get a curve for that degree of freedom. And from that curve, I can compute the p-value. And so for this problem, how do you figure out the degrees of freedom? Well, if the model is fully specified, as in this example, in other words, if we know all the parameters and there's no parameter to estimate from the data, if we know everything from the box, then the degrees of freedom is very easy. You find the number of terms in chi-square, subtract 1. So in our example, there were 6 rows in the table, and so there's 6 terms. When we compute the degrees of freedom, that means that 6 minus 1 is 5. So the reason why it was 5 is because if you have 6 rows and they add up to 60, remember from the table here, there's the sum of all the die, the sum of all the number of rows is 60. So if you look at the frequency, you add them up, they should add up to 60. But only 5 of them can vary freely, because once I have 5, the 6th one is determined by the previous 5. For example, if the sum of the first 5, in fact the sum of the first 5 right here is 51, so this 9 is determined by that. So this 9 doesn't vary freely, only the first 5. So that's why in this case the degrees of freedom is 5. So it's the number of terms minus 1, because the last term is determined by the previous 5. Yeah, so once we know the degrees of freedom is 5, now we can look at the curve, the chi-square curve that corresponds to this degree of freedom, and we can find the p-value by finding the area to the right of 14.2, which is the chi-square statistic that we found. So in the back of your book, this is the table of the chi-square table, and the way that we read this is that we look at the degrees of freedom. Say, for example, this degree of freedom here is 5, and so for each of the column, for example, look for the column under 5%, and the degree of freedom is being 5 here. So this number is 11.07. So what that means is that the area to the right of 11.07, again the area to the right of 11.07 under the curve is going to be 5%. So that's how you the number in the middle tells you the chi-square statistic, and the number on top, the rows on top, tells you the p-value. But the problem is that 14.2, notice, look at the degrees of freedom 5 here. There's no 14.2 here. So 14.2 is not in this table. This table is incomplete. But 14.2 is between 11.07 and 15.09. So that means that 14.2 is somewhere between 5% and 1%. So that you know that the p-value has to be between 1% and 5%. And it's probably closer to 15, so that means it's closer to 1%. Maybe a little bit more than 1%. Okay, so once you use the chi-square test as opposed to the z-test, if it matters how many tickets of each kind are in the box, use chi-square. But if only the average of the box matters, use the z-test. So, yeah, suppose instead if you're picking out a box of tickets from a box, number from 1 to 6, because it matters how many tickets are in the box of each, we want to use the chi-square test. But if you want to know just if we want to test the hypothesis about the average of the box, and we don't care, you know, what kind of tickets are in the box, then we want to use the z-test. So the chi-square test says that whether the data is like the result of drawing at random from a box whose contents are given. The z-test says that, well, whether the data is like the result of drawing at random from a box whose average is given. So let's look at the Wheel of Fortune. So some winners from the California State Lottery are chosen to appear on a TV game show called The Big Spin, and each contestant spin a heavy wheel with 100 slots numbered from 1 to 100. A hard rubber ball bounces around inside the wheel and then settles down onto one slot, determining the prize given to the contestant. So a lot of money at stake, so the wheel has to be tested quite carefully. So the State Lottery Commission's consultant had the operator spin the wheel 800 times and count the number of times the ball lands on each slot, and make sure that the numbers that come up is within reason, and that shows that this is random. So he made a chi-square test of the observed frequency against the expected frequency. The chi statistic in this case, after he computed, happened to be, say, 119. Again, all the calculation is done here is the same as what we've seen earlier. So that means because there's 100 slots, the degree of freedom is 99. You look up the curve for the chi-square curve, we find that p is 8%. So 8% is kind of that, you know, marginal. So 5% is usually where you reject, right? But 8 is kind of there, so it's you know, it's kind of hard to tell. But when they look at the data, they notice that the slot number 69 came up most often and 19 the least often. And these numbers are opposite from each other. So that means that there's some relationship, there's some correlation here between these two, and that means that maybe there's something wrong. We need to look at the wheel, and so to look at the wheel more carefully, and they found out there was a metal weight that was found in the back attached to the rim near the slot 69. So that means that so they took out that so it was used to balance the wheel, and so that caused 69 to come up the most often. So the weight was removed and the wheel was rebalanced, and they run the test again. So when they run the test again, they realized that the wheel, they need to oil the wheel so that it doesn't squeak, but they did that. So finally, after all that, they found out that the chi-square statistic, after they do this, that it works well and that is within chance. And so that's an application of how we can test, you know, whether, especially when you have a test that requires many different categories, you can see whether something is truly random by conducting this test. So here's basically the chi-square test. The basic data, this consists of the number of observations, usually denoted by n. For the die example, we have n was 60. We throw the die 60 times. For the Wheel of Fortune, we did that 800 times. So n is the number of times we observe. We need to have a chance model. This is a chance model that's based on a box of tickets, and then draws are made at random from that box. And so according to the model, the data is like drawn from this box. For the die, the box was from 1 to 6. For the Wheel of Fortune, the box will be from 1 to 100. And then we have to create a frequency table for each value. The observed frequency obtained from the data by counting, and then the expected frequency is obtained by using basic probability. And so once you have the frequency table, we can calculate the chi-square statistic. This is computed from the formula that we saw earlier. So for the die, that statistic was 14.2. For the wheel, it was 119. But we use that same formula. And then we also compute the degrees of freedom. Again, this is one less than the number of terms in the sum. So when we have that, we have the curve. And this is found by looking at the table. You know the degrees of freedom, and we know the chi-square statistic. We can find the p-value. And once we know the p-value, for example, for the die, the p-value is 1.4%, which causes us to reject the null hypothesis. But for the p-value, it's kind of marginal, 8%. Okay, so the chi-square statistic can be used to test the hypothesis that data were generated according to some chance model, and the formula for it is the sum of the observed frequency minus the expected frequency square divided by the expected frequency. When the model is fully specified with no parameters, has to be estimated from the data. The degrees of freedom is the number of terms minus 1. And so we use that chi-square statistic along with the degrees of freedom to come up with to look up a chi-square curve based on those numbers, and then we get the significance level p-value, and from there we can determine whether we should reject the null hypothesis. Okay, that's it. Thank you for watching.